This is section 17.7 and it's about the common ion effect and the effect of pH on solubility, which is basically a fancy name to refer this to as a consequence of Le Chatelier's principle. Okay, because everything that we're going to discuss today is uh, based on Le Chatelier's principle. So how the adding or removing one of the substances that participate in the equilibrium will affect the equilibrium. Okay. So for the most part, this is about how the common ion, if you have a solid that is with limited solubility, if you add a salt that contains an ion that is in common with that insoluble salt, then you are going to decrease the solubility of that salt. So that's the first thing that we need to keep in mind. So adding a common ion to a solution will reduce the solubility of those ionic compounds. So for example, here we have silver chloride, and the molar solubility of silver chloride is 1.33 10 to the negative 5. Okay? The solubility equilibrium for silver chloride is you produce two ions. The silver chloride molecule, if you will separate into one silver ion and one chloride. Now, if you add sodium chloride to that solution, basically what you are doing is adding more chloride to the solution, and therefore what you're doing is you are shifting the equilibrium towards the left, toward the production of the solid. So basically there is less solid that will be dissolved in this solution. That is if you add some sodium chloride. If you add another salt of silver, like if you add more silver nitrate here, the same thing is going to happen. So any salt you add that contains silver or chloride will end up resulting in a decreased solubility of the silver chloride. All right. So how do we incorporate this into our calculations? So let's assume that we have that solution of silver chloride, and well, we want to know if you have a different solution. In this case, difference by different solution, I mean if you have a 0.2 molar sodium chloride solution, how much you can dissolve of the silver chloride in comparison with pure water. So what do we need to do here? So we have our equilibrium, right? AgSCl solid goes to Ag1 plus aqueous plus chloride also aqueous. Okay? And when we build our ice table, then we have to take into consideration how much chloride you have to begin with. All right? So because now initially you have 0.2 of this. And let's call this X. Not excess, but X is the amount of solid that you will be able to dissolve. Okay? Meaning all of that amount X will be dissolved. Therefore, the change for AgCl is going to be minus X. Of course, here is 0. The change for the silver ions is going to be plus 5. And the change for chloride is also going to be plus 5. Alright, so there is no, you basically consume all the solid. Remember, the solid is in excess, but this is just the part that is being dissolved in water. So you end up with X, that's the amount of silver in solution, and then here you have 0.200 plus X. Okay, so now we can compare the KSP here, which is 10 to the negative 10, and then we can pretty much say the same thing. So when you compare that to the initial concentration, it's rather small. Okay, so it's a very little amount that is going to be dissolved. So we can assume that X is small here. So X is small. So that when we write our expression for KSP, which is Ag plus times Cl minus, then we are going to end up with X 0.200 plus X, And basically what we do here is that x is very small in comparison with x. All right, so we reduce our analysis to KSP equal to 0.200 x. Therefore x is simply KSP divided by 0.200. And this is 177 10 to the negative 10 divided by 0.2. And this is equal to, x is going to be equal to 885 10 to the negative 10. Okay, since this is the value, the x is the amount of silver ion that is in solution, and at that point, okay, if this is the amount of silver in solution, this is the solubility. As defined is the solubility. Okay, so what we are comparing here, solubility in 0.200 molar NaCl is equal to 885 10 to the negative 10 versus pure water, which is 133 10 to the negative 5. So the solubility decreased by 5 orders of magnitude here by just having some sodium chloride in the solution. Okay, so that is the impact of the common ion. Now when it comes to pH, well, it's similar in a way, because the main impact would be in the anion, and that is if the anion is a basic anion, if it's a conjugate base. Okay, if it's a weak base, let's put it that way. If it's a strong base, well, weak or strong, they will interact with the pH of the solution. I mean, you will obtain a basic pH, right? So what does pH do? Well, with pH you control the pH by adding acid or base. Therefore, if you are adding acid and you have a basic anion, then naturally that basic anion is going to react with the acid that you are adding. Okay, so that's going to be a neutralization reaction. So in this particular case, we have magnesium hydroxide. And the equilibrium in magnesium hydroxide, you obtain 1 magnesium ion and 2 hydroxides. Okay? So now think about this. If you focus your attention in the hydroxide, and then you are adding H plus to the hydroxide, what is happening here? Well, the hydroxide will react. So H plus or H minus will go to H2O. So you are removing the hydroxide. And what happens if you are removing the hydroxide? If you take this out, what is going to happen to the equilibrium? Well, the equilibrium will shift to the right. Okay, remember Le Chatelier's principle. If you remove one of the components in that equilibrium, the equilibrium will shift in such a way that will replenish what was removed. Okay, if it's removed in the product side, then the equilibrium will shift to the right in order to make more of the products. So that is what happens. So hydroxides, let's put it that way, hydroxides are more soluble in acid media because you are removing the hydroxide. Okay, now if you go to basic pH, okay, in basic pH you are adding OH minus, and the analysis that you follow there is pretty much the same as in the previous slide when we were discussing about the common ion effect. So if you add more OH, then you are adding more of the product there, and then your equilibrium will shift to the left. You will decrease the solubility. So see, if you have metal hydroxides that are not soluble, then in acid pH the solubility will increase. In basic pH the solubility will decrease. Okay, acid pH the solubility goes up. In basic pH the solubility goes down. Okay, and but this solubility goes down mostly for hydroxides. If you have something different from a hydroxide, you may not observe a decrease in solubility at basic pH. All right. So anions that are weak bases and that are different from hydroxides, well, they also their acid-base equilibrium will be affected by the pH and therefore the solubility of the salt that you are working with. So in this example, okay, we have three different compounds here, and we want to know if they will be more soluble in acidic solution than in neutral or basic solution. Basically, the question is asking, the real question is, which one or which ones are more soluble in acid pH. Okay, that's what we are looking for here. So we have a mercury hydroxide. It's a hydroxide, right? So we have mercury, and the equilibrium here would be mercury 2 plus 2 hydroxides. So now, because you have the hydroxide, this is going to be sensitive to high pH and low pH. And what is the impact? If you are at low pH, then you are removing OH minus and the solubility will increase. And if you are at high pH, you are adding, let's put it this way, pH high, you are adding OH minus, and then you shift the reaction to the left. And if you are at low pH, you are removing OH and the equilibrium shift to the right. Okay, so this is more soluble at low pH. Okay, here we are going to focus our attention. Remember, we are talking about the anions. The anions are the main focus of the common ion effect. So copper 1 bromide, so we are focusing our attention in the bromide, right? And the bromide is the base of strong acid. What does that mean? This doesn't have no base equilibrium. And if there are no base equilibrium, then this salt is neutral and the solubility is unaffected by pH. So you may have acid pH, you may have basic pH, but the solubility of that salt will remain unchanged. Something else may happen, but in terms of the solubility of that particular salt will not be affected by the changing pH. Okay. Now cadmium fluoride. We focus our attention on the anion, correct? So we have fluoride here, right? And fluoride in presence of acid will give you HF. So adding H plus, which is also the same thing as decreased pH, remove fluoride. And as such, increase the solubility of the salt. Increase solubility. Okay, so cadmium fluoride is more soluble at low pH. All right. So from the point of view, for the conceptual point of view, so you have to look at whether the anion have acid-base equilibria, and then from that you can determine if there's going to be an impact of pH on the solubility of that salt. If the salt is neutral, then the pH is not going to affect the solubility of that salt. And if the anion is basic, then yes, they're going to be more soluble in acid media than they will be in basic media. All right. So last example that we have here, what if we have sodium hydroxide, not sodium hydroxide, nickel hydroxide, and we want to know what the pH, what the solubility at pH 4 is, right? So what do we need here? So our equilibria is nickel hydroxide that goes in, let's do this formally, right? So this is a solid that goes into nickel 2 plus dissolved state plus 2 hydroxides in dissolved state. Okay, now in this case, because we are using a pH, so if pH is equal to 4, then it means that the POH is equal to 14 minus 4, and that is 10. From here, the concentration of OH minus is going to be 10 to a negative 10. So in our equilibrium, we are going to set this concentration equal to 10 to a negative 10. Okay? And then, pretty much KSP is going to be the concentration of nickel, 2 plus, times the concentration of OH minus square, because now you have 2 here. Alright? So technically, how much nickel you can dissolve will represent the solubility of nickel hydroxide here. Therefore, the concentration of nickel 2 plus is equal to KSP divided by the concentration of OH minus square. Therefore, concentration of nickel 2 plus is equal to KSP. Well, we're supposed to use the numbers now. 548 10 to a negative 16 divided by 10 to a negative 10 raised to the power of 2. And from here you obtain 548 10 to a negative 4. This is molar, and yes, this is a huge solubility. Okay, so theoretically, okay, this is solubility at pH 4 if you could maintain the pH constantly at 4. Okay, now think about it. You have a pH, you have a given concentration of protons at that pH, correct? 10 to the negative 4 to be exact. So if you keep adding this compound, it's going to neutralize the proton concentration, right? So the pH is going to change, the pH is going to go up. So you can't really add nickel hydroxide to that concentration because you will consume the protons. Okay, you will affect the pH by adding this substance to the solution. You are increasing the pH and the solubility will go down. Okay, but again, this is theoretically, so you should be able, if you could somehow maintain the pH constant at 4, then you should be able to dissolve 5.48 10 to the power 4 molar concentration of nickel hydroxide. Okay, so don't be afraid if you get a big number. Okay, because, well, that's what the calculation gives you. That's what the calculation predicts. Okay, that you should have that concentration. What it means really is that nickel hydroxide will be very, very soluble at pH 4. Okay,